Hello class, this is Mr. Hunter again, and I'm here to talk to you about forces and forces as vectors. We've been talking about Newton's first and second law in class, and we've been analyzing some situations where we've been taking the tension of ropes and trying to analyze how much tension's in the rope dependent on the angle that it's at, as well as the force due to gravity that's on that rope. So just a brief review, remember that vectors have a magnitude and direction. So if we draw an arrow here and label this A, this vector has two components. It has an x and a y component. And so the x component goes in this direction and the y component goes in this direction. And we'll label them accordingly, and we'll say this is A of x and this is A of y. And here's our angle. So if you're given an angle and a vector, we have to use trigonometry to find the sides, or we can also use the law of sines to find the side. In this case, we'll use trigonometry, so SOHCAHTOA. And I know that sine of theta equals A of y over A. In most cases, you'll hear sine is opposite over hypotenuse, and A of y is our opposite, and A is our hypotenuse. Or you'll have cosine of theta equals A of x over A, which once again, A of x is our adjacent, and A is our hypotenuse. And we also have tangent of theta equals A of y, which is opposite, over A of x, which is our adjacent. With vectors, it's important to note that whenever we're given a resultant, we're going to usually, not in all cases, but usually want to break up that resultant vector into its x and its y component. So let's put some numbers to this. Let's say that you were given this triangle and you were told that A equals 10 newtons, and that you were told that theta equals 30 degrees. You're then asked to find A of x and A of y. Oh, something I forgot to mention. We can simplify this above triangle by just doing simple math and just cross multiplying, so that A of y equals A times sine of theta, and A of x equals A times cosine of theta. And that will help us in a second. So in order to find A of y, I've just been given A, and I've just been given my theta, so we can actually plug them right into this equation. And in this equation, I have A of y equals 5 newtons times sine of 30, and that equals 5 newtons, because as we know, sine of 30 equals 1. And for A of x equals 5 newtons times the cosine of 30, and that will equal 8.6 newtons. If you notice, we have two significant figures, or one significant figure, excuse me. We were told, I just did my math wrong. A is 10 newtons. Go, Mr. Hunter. Sorry. This is 10 newtons, and sine of 30 is 1/2. So, if you're watching, please make sure you change those notes. My apologies. So we now have A of x and A of y to be 5 newtons, and A of y is 5 newtons, and A of x is 8.6 newtons. So now let's apply this to a tension and force problem. Let's say that we have a block hanging off of a piece of rope attached to the wall. And the block weighs 100 newtons. And what I'd like you to do is find the force of tension in this row. This block is not moving, which means that it's in equilibrium. Which means that our force net has to equal 0. So there's a 3 or 4 step process that I would like you to write down in your notes when trying to solve problems like these. One is draw the free body diagram. In this case, our mass is 100 newtons. Well, it's 100 kilograms. A force due to gravity makes it 100 newtons. And so that arrow is going down because we have gravity pulling down on it. And we have the force of, we have the force of tension pulling back up on it. So for the second part, for step 2, so this is step 1, and this is going to be step 2. When possible, break up resultant force vectors into its x and y component. This will be useful for later because, remember, vectors can only be added or subtracted or on the same plane. So we can only add y vectors together, and we can only add x vectors together. And step 3, in this case, all of our vectors are on the y. We don't have anything going to the left or right, or we don't have anything at an angle. We just have straight up and straight down, and so these are both y component vectors. So we don't necessarily need to do step 3 or step 2 because they're already broken up into its x and y components. So if the system is in equilibrium, we need to make sure that we sum all forces in that direction and set them equal to 0. Because we know that our F net, or our force, all of the sum of our forces, are 0. And this applies to both x and y direction. So in this case, I have F y net equal to 0. And then now I look at my free body diagram and I determine what forces I have acting on my y. So I have a tension force that's pulling up, and let's say up is positive. So this will equal the tension force and minus the force due to gravity because it's in the opposite direction. And so now I can just plug and chug to solve. I know that my force of gravity is 100 newtons. So then I have T minus 100 newtons equals 0. So I get T equal to 100 newtons. Once again, it's in equilibrium, so it's equal and opposite forces.